All right, recordings rolling. We're getting close to the end of class. You guys have a bunch of data, so I'm getting questions about how do you calculate momentum before and after and kinetic energy before and after. So let's say I have this, for example. So I got these two carts that could boing bounce off each other. Okay, and they do bounce off pretty elastically. Say my cart A has a mass of 1.5 kilograms, and my cart B has mass of just 0.5 kilograms because it's just an empty cart. Guys, it. And I got this numbers recorded right here. Here's math A, here's math B. Guys see that? That's exactly what you're looking at. Guys see that? All right. So I'm going to put these to the side. Okay. All right. Now, let's say you got the first cart rolling and it goes through the speed gate and reaches 2.4 meters per second. And the other cart is just sitting there at rest. And then, boing, they bounce off each other. And then after they bounce off each other, well, guys, think about this practically, and maybe you guys just kind of figure this out too. Actually, try this out. If you have a huge cart slamming into a small cart, like how do you think that both carts are going to roll into the right?
Yes.
Yeah, it's got to kind of plow through. So I think post collision, the velocities will still be positive. Right? Now this one did. It looks like the heavy cart did slow down a little bit, and the lighter cart, really took off. Now it's going really fast. So you may have seen that too. If you slammed a heavy cart to a small cart, maybe a small cart, like really took off. Okay. So how do you calculate momentum? Because what does the sigma mean right here? This jaggedy looking symbol is called sigma. It means summation. It means you add up. So we're adding up the momentum before. And momentum, of course, is mass times velocity. So I need for cart A and for cart B. So momentum pre-collision would go mass of cart A, 1.5 kilograms, and just pop in the number, times this pre-collision velocity of 2.4 meters per second, plus, and then cart B was 0.5 kilogram mass, but it was at rest, so it didn't actually add to the momentum. Okay, so that doesn't count for anything anyway. But what's 1.5 plus 2. Times 2.4? Okay. So the sum of momentum before collision was 3.6 kilogram meter per second. Yeah. So the unit is kilograms meter per second, and the number here happens to be 3.6. Okay. Right, you guys Now, after the collision, I can do something similar. Sum of momentum post collision. Okay. I can say, well, it's still 1.5 kilogram mass on mass A, but now mass A is only going 1.2 meters per second. 1.2 meters per second. Plus, my other car was 0.5 kilograms. Now this one actually is moving. It's moving at 3.6 meters per second. Is that okay? Okay, so see where I'm getting all these numbers from? How it's all feeding into these equations? Okay. So I'm figuring out what's the sum of momentum plus collision. Sum of means I'm adding. And momentum is mass times velocity. There's cart A, there's cart B. Put it together. So let's do 1.5 times 1.2 plus 0.5 times 3.6. Okay. And I get, oh, look at that. 3.6 kilograms meter per second. Huh, that's interesting. This whole thing is 3.6 kilogram meter per second. Okay. So it looks like my momentum actually was conserved. So this is a really ideal scenario, isn't it? Guess it? Okay. And you guys should have gotten something kind of close to that. If this number is 3.6, you should have gotten maybe somewhere between 3.6 idea. Okay. Okay. Even better if it's exactly conserved. How about kinetic energy? Well, I know kinetic energy is something like 1/2 mv squared. Now this one, anytime you square the speed, it becomes positive regardless. So even if you had the carts rolling towards each other and you had negative velocities, that doesn't show up in the kinetic energy data. Kinetic energy is going to be a straight positive number. So sum of kinetic energy before the collision, that'd be 1/2 mass A is 1.5 kilograms times its speed of 2.4 meters per second. That's being squared. And I'll just say 0 joules for cart B because it had 0 speed, so it doesn't add any energy to the system. So it's 1/2 times 1.5 times 2.4 squared. That is 4.32 joules. So energy is in joules, 4.32. Okay. So leading up to the collision, I had 4.32 joules of mechanical energy in that system. Okay. Now, if this is truly elastic, then kinetic energy ideally should be conserved. And you either found that today or it maybe decreased a tiny bit, okay? But it should be fairly comparable. let's see how my numbers play out. What's sum of kinetic energy post collision? So that's 1/2, 1.5 kilograms going at now post collision it was only 1.2 meters per second. Right, that's being squared plus 1/2. The other mass was 0.5 kilograms, and let's say that was going 3.6 meters per second. And then you're going to square that. Okay, what does that come out to? Let's say what's 1/2, 1.5, 1.2 squared plus 1/2, 0.5, 3.6 squared. That's, oh, look at that. It's 4.32 joules. 4.32 joules. Okay. So I have a really textbook ideal scenario because the kinetic energy was also conserved. And for an elastic collision, that should be the case. Yeah, so here's a numerical example.